Hello everyone and welcome to this new solo engineer video. Today I'm going to show you how to simulate a PCB. For instance, in this case, I want to simulate some traces for GPS antenna here. And so I'm going to show you how to extract this with CST, a software that is used to do 3D EM simulations. And so the first thing we're going to do, we're going to remove most of the circuit because this is going to be too much for one simulation. So we're just going to restrain this area. So we're going to remove most of the PCB so that the simulation takes it's going to be much faster. And then we're going to I'm going to show you how to set up the ports for the different components that we want to probe. So here, for instance, we have a capacitor, we have an inductor, some shunt capacitors, and we also have the U-blocks module and the GPS antenna. So I'm going to show you how to place a port and how to set up the simulation in CST. And so this is for a GPS module from the company U-blocks. So we're looking at frequencies around 1.5 gigahertz, so between 1 and 2 gigahertz range. And so the traces that I have here are supposed to be 50 ohms. So that's what also we're going to look into from the simulation, if it's really good, low insertion loss and a good return loss for these traces to minimize the losses, and also so that you know this is only a 2-layer PCB on FR4. So the traces, for instance, I'm using 39 mils, so 39 mils in width, and with 6 mils of clearance, with a coplanar waveguide with vias around it. So that's what you see here. So I already set up a video. You can look into my YouTube channel for it, how to export Altium Designer PCBs like this one and import it into CST. I just follow the steps that I show you in the other video. So if that interests you, you can go and watch it first, and then from here we're just gonna go ahead and work in CST how to set up the simulation. Alright, so the first thing, like I said, we want to remove most of the circuit board that are not of interest. So the part that is of interest is located here. So we want to simulate this part, so we probably want to cut most of the PCB here. So let me show you how we're gonna do it. So first, one thing we can notice is that every trace that is imported into CST is created as a different net. So we have all these different nets here that are independent, are all different. So one thing we want to do, at least one thing that I found was working well, was to select here copper, and we're gonna select all solid in this material. And as you can see, it goes into the tree here and select all the different nets that are in the same material. So for instance here, all copper, because there are traces on my PCB. So what I want to do is select all, well, make sure they are all selected, and go ahead here, and we're going to do add. So now what this does is that it creates only one layer, so one component, for all the different traces, instead of having different objects. So we want to do the same for the vias, because all the vias are independent because of the different net names. So again, we're going to select all solid in this material here, and we're going to do the same thing. We're going to add them here, so it's all combined into one object. So now, as you can see, we went from all these different nets, because these are basically empty folders, so we can go ahead and delete these here like that. And so we still have our PCB here with the top, basically the top copper, and the different vias, top and bottom copper actually. So as you can see here, I didn't change anything in my PCB. I just combine all the different traces objects into one. And that's going to be easier than for removing part of the circuit. So if I put my oriented front, for instance, here like that, and then I can do create a rectangle, for instance, and let's say I want to select here to about here, and then 3D wise, I can put this rectangle much bigger. Click, and then we're gonna create a new component, new material. Okay, it's just used for removal, so we just want to use this, cancel here. So we just want to use this rectangle to remove the circuit. So like we want to do a subtraction of this rectangle and whatever is underneath. So we're going to go ahead and select these two here. We're going to go here and select subtract, and then we're going to double click on this rectangle. And as you can see here at the top, it says press return to confirm. So I'm just going to press enter, and as you can see, it just removed all my traces. So what's left actually is the substrate, because I could have, if I go back, I could have selected also the substrate and do it as at the same time. And I think that's what we're gonna do, because we want to cut it with the different layers and the vias. Okay, so I'm gonna start over here, but instead of selecting only this one and that one, I'm also gonna select my substrate. So all my different layers of substrate, and yeah, I think I'm just gonna select that. And then again, I go ahead, subtract, and either you double click on the solid, or you can go and pick the solid here, because we created a new component here, and then you press confirm again. And as you can see, all my right side of my PCB just disappeared. And so we want to do the same thing here at the bottom, and after that we're going to remove all these different components that later. So let's go ahead and first remove the bottom part. So so probably something like that, and then again whatever the height. So we want to assign it to this new component, new material that we created. Press OK, then cancel, and then we got to select everything again here, and then we do a subtract, and we click on solid one, and we press enter. So as you can see here, now my PCB is much smaller, so that means that my simulation time will be increased, will be much faster, because the simulation will only happen on this part of the PCB, instead of trying to extract all the different interaction with the other traces. So whenever you do a 3D simulation, try to minimize or reduce the component size, or at least the simulation area, so you increase simulation time on overall, because you don't need necessarily to know what the interaction is with the other traces. So now we have some components that were imported from Altium to CST. So all these different ports. So what I want to do is I'm going to select all of them, and then I'm just going to remove. I just want to keep these ones in the end. So I can select everyone and then unselect, for instance, C12, L1, R27, C13, and C14. And as you can see, all the other ones are selected. I'm just going to go ahead and delete, like so. All right, so I think I forgot to select these little sheets when I did the subtraction, so I can just go ahead and try this again. I create a solid here, and then this new component from my dummy material. Okay, and then if I select lead and then I click subtract with my solid, for instance, yeah, it removed these. So we could have selected leads as well, which are perfect conductor, electrical conductor sheets, and those are used for to connect the ports of the components. So we don't need these, especially those that are outside of the region of simulation. So we're just going to select these again, do this same procedure, cancel, and then leads, Boolean, subtract, and then solid, enter. All right, so now we're left with the PCB that we are interested in. And actually there's still two leads here that I I don't need, and it's kind of far from my simulation, so I'm just gonna short it. I'm just gonna remove that part as well to make things a little bit easier, so I can cut it here. So again, I'm gonna select all my different layers here and then click subtract and then solid one and then press enter here. So as you can see now, I think we have something I'm good with, and I'm gonna hide the substrate here so we can look only at the PCB. All right, so now it looks like something we're going to be able to simulate easily. And if I go back to my Altium, so we have an antenna input here. So I said antenna input, that's the name of my net, but basically it's the output, it's the input of the RF signal for the antenna. So the antenna comes here on this UFL connector, goes through a capacitor, a DC blocking capacitor, and then goes to the antenna input port. And then we have a VCC RF, which is the supply for this node here, for the RF node. And it has like a series resistor, some decoupling capacitor, and a series inductor here to bias this to bias the antenna port. So yeah, so if we go back here, that's exactly what we have here. We have some component here, 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 and here. And then so what we want to do is put ports on the different parts so we can create SNP and then simulate that in some other software with these different components, see how it behaves. So what we're going to do here, we're going to start putting some ports. And actually, I might also want to remove these ports, even though earlier I kept them. I want to remove these because these are lumped element, and lumped element means there are a fixed element, for instance, a 100 ohm resistor or a 1 microfarad capacitor. But in my case, I might want to, instead of importing them in my simulation, I might just want to create a port and then add it later in my, let's say, ADS simulation, and then I can fine-tune what capacitor value would be best. So I want to delete that again, but one thing here is that I want to keep the sheets, because these are essentially where the capacitor or resistor or inductor will be when I assemble the board. So that's exactly where I'm going to put my ports. So let's go ahead and click here, and let's put a first port, let's say, on my antenna input here. So again, select the ground plane before, and then after that we select the edge, and then we go ahead here and select discrete port, and then we can label it antenna in and click apply. So as you can see here, it created an RF port 1 here on the U-Blocks connector, U-Blocks pin here. After that, I might want to put a port on the RF UFL right here. So click the ground, click the edge, discrete port, and then the UFL port. Okay, so far I have port 1, port 2, and then what else? After that, I think I might have one port here. Like this here. And then it's going to be my VCC RF. And for the other ones, actually, it's going to be, I'm going to use the sheets that are here where my components are going to be. So again, I can select edge to edge, for instance, here to here, and then select the discrete port, and then this one's going to be C, I'm going to call it C antenna. All right, so I fast forward a little bit because it was the same process for all the different ports. So now I have my antenna in here. I have my UFL port, which is the input of my GPS antenna, for instance, on my UFL connector, and then I have a VCC RF pin here, which is the bias supply for my antenna, and then my different components, for which my capacitor, my inductor, my resistor, and my two other capacitor, for which I put ports on it. And then I'm going to show you in ADS how to connect real components like a real capacitor to these ports, so we can do a full simulation of these different components. So now the only thing left is to set up my simulation. So again, we set up the frequency. I usually set the minimum frequency to about 100 megahertz, and then the maximum frequency usually about twice my frequency. So instance, here it's 1 to 2 gigahertz, so I can two times would be about 4 gigahertz, so I can go a little bit higher and set 5 gigahertz here, just to make sure I capture everything down to 1 or 2 gigahertz correctly. And then after that, my background, just like my other simulation, I want to put a normal background. And then for my boundaries, I'm gonna apply some space. And like I said earlier in my previous video, I'm just gonna use 4 or 2, which should be good enough. So if I look at my boundaries, you can see that my simulation boundaries are much bigger than my simulation area here, and that should be open space, which shouldn't influence any of the EM simulation. So the next thing I want to do, I might want to do monitor some field, for instance, at 1 gigahertz or 1.5 gigahertz. So I'm just gonna save the E field and the H field, and then one last thing before we set up the simulation is just to make sure it's frequency domain solver, and then in the settings we can just leave everything by default, and it has some adaptive mesh refinement. So until it's going to reach 0.02 in the S parameter, it should go with smaller mesh. So let's go ahead and hit start, and then we're gonna let it run and see what the results are once it's over. All right, so our simulation is over. So what we're gonna do, we're gonna export the touchstone, which is the SNP, the S parameter file of all these different ports. So we have 8 ports here, 1 through 8. So that will generate us a S8P, and then we can use that 8SP, so a 8-port SNP file that we can use in other software like ADS to generate to analyze the performance of our simulation here with the different components. So that's what I'm going to show you up next. So I just said that the simulation probably took somewhere around 10-20 minutes, not even 20 minutes, maybe 15. So that was pretty quick. And if we, for instance, had done the simulation with the full PCB, just like the complete Altium PCB, like here, it would have taken, I ran it before, and it would have taken almost a full day. So that's how much we can save in simulation time without affecting the performance, just by reducing the size of our simulation area. So now I jump to ADS real quick with the S8P here, my S parameter of my my simulation that I did in CST. I just created a port here and imported my file, and as you can see, I just labeled the different ports. So port 1 corresponds to my antenna in, port 2 UFL port, etc., etc. I just labeled them here, and then I set up my ports, my 50 ohm ports, to antenna in, UFL port, and my VCC RF, and all the other ports are set to my different components. So I won't explain in this video why I set up my ports to a component and then to ground to mimic the connections that I made here. Just know that that's how I did it, and I can explain it in some future video. But yeah, so basically I want these components, for instance here, 40 7 picofarad capacitor for my series capacitor, and then my inductor is 33 nanohenry, and then I'm using other capacitors here for DC for decoupling capacitor. Those are the ones that I set up here for on port 7 and 8, and my resistor here, port 6, is set up to 10 ohms. And then I can use this here, my simulation in ADS, to run. If I hit run, and then I can look at the result depending on whatever component I'm using, I can see the performance. So if I'm looking at port, so the insertion loss from 2 to 1, so that would be equivalent of looking at my U blocks port here up to my UFL port here, port 2 to 1, through that series DC blocking capacitor of 47 picofarad. I'm looking at something like 0.12 dB insertion loss, which is pretty good for FR4 PCB. I can look also at my matching. So for instance, I look at S11 and S22, so my return loss, and I can look into different frequency, but for instance, I'm interested in my 1 gigahertz, so 1.3 gigahertz. It's pretty well matched to my 50 ohms, at least for S11. S22 is probably also similar, 1.5 gig, and we can kind of see it here where my insertion loss would be best at 1.3 gigahertz, and this is fine because my Wi-Fi, the GPS signal, there's different bands, and one of the band is in the lower gigahertz, so 1.1, around 1.1 gigahertz, and the other band is around 1.5 gigahertz. So that covers with good return loss both bands, and also good insertion loss for both bands. So up to 0.15 dB insertion loss, which is really good. And if I'm looking at here, I can see that my 3.1 and 3.2, this is my connection to the VCC port for my bias, and I can see that there's a big isolation on that DC port up to my RF path. So it means I have more than 30 dB isolation from the DC to the RF. So this is also pretty good. So in the end, this is what I wanted to show you today: how to take an Altium Designer project into a CST, reduce the board size so we can optimize the simulation to the specific area we're interested in, placing the different ports, and then running the simulation. And then after that, I just showed you how to import the data into ADS so we can analyze the data and make some conclusion if we need to rework the design, or if it's good enough, we can fine-tune the RCL components to optimize the performance. So I hope you liked the video. Don't forget to like and share the video if to other people that you think are interested in that subject, and I'll see you again in another solo engineer video. Thanks.